again, but when a proper working roots of a non-linear equation. Now you may be thinking where we have discussed this thing. So if you remember the introductory lecture that I have formulated, so so we have discussed that part, that what are the root or roots of the lecture, the first live session I was referring. But let's continue this roots of a nonlinear equations. So this is our topic number. If we go in a sequence of the course content of this lecture, then we can say that this is our topic number 3. The first one is error and error representation. The second one is operators and difference equation. And then we are heading towards the roots of a nonlinear equation. Okay, so let's discuss there that what type of what we have to cover in this topic. Okay, so this is the heading, and this heading consists of few keywords that we have to figure out again. One is a nonlinear, and we all know equation is something right hand equal to left hand in the mathematical terms. But what is nonlinear? And then the question is what a root and roots. So there are two things. So first, let's understand the nonlinear or linear function. So for example, student, if there is any function y equal to f of x given to you, and this is the function where x is independent and y is dependent. You all know very well from the calculus classes. So if, and this is the equation, right hand equal to left hand. For example, I'm going to write something like x square plus 1, or maybe y equal to 2x minus 1 or something like that. So these are other, and other examples could be added as well. These are the examples of the function. But if I want to classify that whether this function is linear or non-linear, and what could we do to understand that? So for that we have a very simple idea, and there are two ways. One is the graphical way, but we do not usually like to make a graph of each function. Other way is we have to analyze the function in such a way that if we compute the derivative of this function, whatever be the function, and derivative of that function, whatever the function is given to you, and you, or equation that you want to verify that whether it's a linear or a non-linear, the idea is you just need to find its derivative first order. And whatever be the derivative comes, you have two possibilities. Either you will get a constant answer or a variable answer. Okay, you have two possibilities. I'm not going so you have a function there, you find the derivative first order, and you get two possible answer, either a constant answer or a variable answer. With variable I mean you will get a derivative in such that it is still depending on the variable, whatever be the variable involved in it, which means that the derivative can change point to point. Okay, this means that the rate of change of y with respect to x is varying with respect to the location. So in that case we can say that, so, and let do not define yet, but let's say there are two possibilities. So there is an equation, I want to check whether linear or non-linear. I compute this first order derivative so that I want to notice the change in y with respect to x, and I got certain answer. So answer could be of two possible. Either it will be a constant like 4 minus 4 0.3 0.9 or 1 billion, it will be a fixed value, or I will get a variable answer, I mean a derivative in the form of function again. So in both cases, how do we classify that? So idea is quite simple. So whenever you get a constant answer, this means that the y is changing with respect to x linearly, okay, with the same proportion. So that's why there is no change. So what you got constant answer, so in that case we call it the function is, or the equation is linear. And if you are getting an answer which is dependent, it is changing at different locations, at different time it is changing, at different position, that there is a different rate of change. So in that case basically you are getting a non-linear behavior. Okay, so not with the constant, but derivative is constant which represent linear. How if I got a derivative of any function which is constant, then how I can say that is a linear behavior? Linear could also be defined like that, if the dependent and dependent are connected such that that we are getting a same amount of change in dependent as we make same amount of change in y, they have having a same proportion of change. But in variable like non-linear equations, we do not have a same amount of change. Let me explain it further. So constant is linear. Easiest way is just compute the derivative. It is constant, then it is a linear equation. Linear, and if not, then it will be a variable, then it will be a non-linear equation. But how do you classify that? For example, these are the two examples that I selected earlier. So if I take the derivative of this function, so dy over dx, it is very easy. So this will be a 2x. And if I compute the derivative of this function, which is if all of you can recognize is the equation of a straight line, so you will get dy over dx equal to 2 only. So which one is what category? So we can say that if I differentiate that function with respect to x, so I will get a constant answer. Okay, and if I differentiate that function with respect to x, I got something variable answer because the derivative is depending on x. For example, if I ask you to compute the derivative at x equal to 1, so you put 1 there, you will get 2. If I ask you to compute the derivative x equal to 4, so you put 4 there, so you get 4. So, and if similarly if I ask you 3, then you will get 6. So it is has a different proportion of working. Okay, so we cannot consider them as a linear function. It is a quadratic function in generally usually we call it, but they have a category as a non-linear function. They are not linear. And easiest way is if you can plot a graph, and if you got a graph of the function like that, a straight line, exactly straight, like when that if you make a certain amount of change in x quantity, you will get at any point you will get a proportional amount of change in a y quantity. Similarly, if you make a same amount of change at somewhere else, then you will get a same proportion of change in a y. That is, y is changing with respect to x in a proportion, same proportion throughout. So in that case, this is an example of a linear function. And we all know if we compute the derivative of a linear, we got constant. So either we can plot the graph or we can do this calculation, which but however, for this equation, which is a quadratic, we all know the graph of this something like, I don't know exact graph, but somewhere like parabolic, y equal to x square. So we can clearly see the change is not uniform throughout the graph along the graph. So this means that it's a non-linear case. Okay, so this is very easiest way to understand whether the equation is linear or non-linear. I'm not talking about the differential equation at the moment. I'm just talking about the function. So whenever the function is given to you, something like that, which you have to have many times in this course onward. So this means that if you want to verify whether linear or linear, you have to look about this simple calculation. Okay, so if that calculation you done, then based on that you can classify it as a linear or a non-linear. Okay, this is just a brainstorming for the topic. So we are discussing a topic called roots of a non-linear equations. So non-linear, we understand that now we have some functions that is changing with respect to x, that is independent variable, with not uniform way, like it is not like uniform. And what we have to do for that function, we have to compute this roots. Okay, this is the new thing. We have to compute the roots. So what are the roots? So let me cover that part also in this small like call it brainstorming session. So what are the roots as well? So root is basically a very simple concept. For example, if I plot any non-linear function, so we know that its graph is not a straight line anymore. It will be a something bending curves or something like that. So for example, I plot a graph of certain function which I don't know, but assume that it is a non-linear. So it will be appearing something like that. So there is a function y equal to f of x, and I plot its graph and I got the following graph. So the point where it is cutting the graph is basically is called the root of the function. Let's call it xr. So what is x root r for the root? So what is the advantage? What is the characteristic of this function? Because I can select any point that can satisfy this equation. If I select this point, I will put there, I will get certain height, positive or maybe a negative as well if it is downward. Okay, but what's the importance of this xr at the moment? The point is that if I put xr into the given equation, I will get y height equal to 0. That is the dependent value is 0. So then what is the definition of the root or a roots? It could be a more than one as well. In that case, we will call it roots. But if it is a single root, then this is how we can define. So fxr equal to 0. Okay. Keep in mind that student, if the equation is linear, which we are not discussing at the moment, we can only have a single root if it is possible then. Okay. But For non-linear, you can have one root or more than one root or no root at all. It depends on the situation. So that's what we have to discuss in this topic as well. So what are the roots? Roots are just the values of x independent variable, such that when you plug that value in the equation, you will get exactly answer equal to 0. That is, there is no y height. So if I go there, I will get certain height, certain height, certain height, but at this point I will get no height at all. Okay, so in this case we understand that, okay, this is the case of a root. So how do we define the roots? Roots are not roots. Root are the value, sorry, value in the domain, or a member of a domain. A proper word could be like that, member of a domain, such that it maps y, that is independent variable. It maps to range equal to 0. Okay, so if we talk with reference to the mathematical part, then what we want to say, we want to say that, okay, these are just a normal x values, that is a member of a domain, but they have a special characteristic. They map to a dependent variable equal to 0. Okay, so for example, if you have any function x, any value x that you put in a function, what which could be a non-linear function, you get it equal to 0. So if you got this answer, then you want to you basically want it to say x is a root. Okay, so this is the easiest way to remember. Okay, now why we have to discuss this thing and what we have to discuss? So we have a many situations, like in which we have to solve equations which are non-linear in nature. Okay, so we know the criteria, but what are the non-linear equations are, and solving means we have to find the root of that non-linear equations, that is those values of independent variable that makes dependent variable equal to 0. So how do we do that? But let me give you some examples. What could be the nonlinear equations are? For example, this is the nonlinear equation. For example, this is the nonlinear equation. Okay, so these are the two examples, and so on. Sin x, ln x, you can make so many functions. But this type of nonlinear equations we all familiar, and we call it polynomials. What we call it? Polynomials. And in this case, it is a polynomial of degree 3. I hope you have learned this in a calculus class. Similarly, this is also a nonlinear equation, because if you compute the derivative of this function, you will not get a constant answer. So in this case, that is this is also a nonlinear, but we do not call it polynomial. We call it a different type of function and call it transcendental transcendental dental functions. What we call it? Transcendental functions. So in our case, we can broadly classify nonlinear equations to two types. One are called polynomials of certain degree. In this case, it's the third degree. So we know we have much more information about the polynomials. Like we know that we don't know exact methods to find the root of the equation after a certain degree, let's say 4 or 5 degrees, but we know that all the polynomials who has a degree 3, 4, or 5, they have an exact amount of roots. Whether they are repeated, complex, or combination of these two, we are not discussing that part, but we have a good some information about it. But however, in the case of transcendental equations, we don't know that whether how many roots that equation exists. But that is for sure, if root exists, it could be a multiple roots as well, but we don't know exactly. So however, they both are classified as a nonlinear equation, but this is not the definition of the transcendental equation. Okay, this is just a criteria of the comparison between the polynomial and the transcendental. So for example, if you have an equation y equal to x ln x plus something pi to something. So this equation is also regarded as a non-linear equation, and not only that, it is a non-linear equation, and not only that, this equation is also called a transcendental type. Now question is, then what is exactly transcendental? Okay, we know the problem now. We have some equations which is non-linear, that is their derivatives are not constant, and we need to find its root, and root are those values which map the dependent value to a zero, independent value to a dependent value, and dependent value must be a zero in this case. So okay, we understand, but what is a transcendental by definition then properly? So transcendental equations are those equations usually which cannot represent the answer exactly. For example, we all know that this equation has a parameter e, which is called Euler's number, and this has something 2 point, I think 17 or 71, I don't remember, to 8 something value, which is irrational. It will continue further. So if I put any constant of like this in the equation, then I never get an exact answer in this case. Similarly, this is a pi involved in it. This is gonna say we can have a log or sine or some value. So similarly, we can have those values too. So in that case, we do not have what do you call it? We do not have a exact representation of our answer. So these type of equations, they are usually called transcendental, but for us it is just a nonlinear equations. Okay, so it is not always necessary that you have a nonlinear equation in the form of polynomials. No, you can have a nonlinear equation in the form of exponential function or logarithmic functions as well. Okay, so this is just a brief review that I have made about the key concept that I'm going to use many times onward. So now what we have to do, student, in this basically the topic, we have to learn few methods that can help us to find the roots, okay, of the non-linear equation. And now I do not need to explain all these things. What is root, non-linear equation? It will be appearing many times. You have to focus accordingly. Okay, so it could be a polynomial, it could be a transcendental, or it could be any other equation, but it has to be a non-linear. So the first methods for finding roots of non-linear equation. One thing before starting this, as this is the end of the lecture number 5 near, but I want to say we will discuss a few concepts there, and then lecture number 6 is primarily focusing on these methods. So I will try to introduce most of the methods and their drawbacks, that why we need this method and what are the drawbacks of this method. That's why we need another method, which method is fast, which method is slow, and what on what grounds we are discussing this thing that which is fast and slow. So we will discuss all the details in the lecture number 6. But the point is that we are entering in a different framework of the course, because in the beginning I said that we are mostly discussing with the approximations, approximate roots. Okay, in a live session I also explained this thing. So what we are referring now is basically we need to compute uh, a roots or a root depending of a nonlinear equation. Okay, so the for that we have a specific methods design. So I'm starting with one of the basic method, and I have a explicit reasons to start with this method, although it is also included in the course, but I have a reason for it, because this method will introduce a concept of approximations, iterations, and successive approximation. That what does this means for us for rest of the topic as well, and this is also very easy to understand as well. So the first method is called bisection bisection method, or sometimes this method is called interval halving method. This is L. Okay, halving method, that is halving the interval. So bisection method, or sometimes called interval halving method. What is this method is for, and what's the reason? However, I have not told you the reason behind it. Why do we need method? Because calculator can do the same thing, a computer can do the same thing, but you should keep in mind that in case of polynomials, at a certain degree we do not have an exact method to find the roots. This is what we have discussed in the live session in the beginning. So if we do not have a method, exact method to find the roots, for example, if it is a quadratic equation, so you all know how to apply the quadratic formula. It will always give you the root, all of the roots, whether it's a real, repeated, complex, and whatever, irrespective of the coefficients of a, b, c that you usually have in a quadratic formula, provided that the coefficient of x square is not zero, which is obviously. So you can compute the root exactly in that case. But as you move higher degree, third order, fourth order, or maybe a decimal degrees, you do not have an exact method to compute the roots. For example, a fifth order polynomial given to you. Can you name, and you can pause the video and think about it. Can you name any method that can give you the exact root of a fifth order polynomial? Like, for example, maybe you are thinking about synthetic division, or you are thinking about the remainder theorem or something, but you should remember that to start this method you need at least one root exactly. So if you don't know the one root, then you cannot apply those methods. So that's what I am referring. Now we are dealing to the problem that are general, and all those methods that we have just referred to you, like interval halving, they are related to the polynomials only. And I just show you that non-linear equation does not means only polynomials. It could be a transcendental equations as well. So in that case, we do not even know how many roots exist. We have not much information available. So how do we handle this thing? So we have an other technique that is purely based on the concept which I already introduced to you, called approximations. Okay, approximations. That is, if we cannot compute the root, is there any way that we can find a value which is very close to the root? Because the definition of the root is quite clear. If you want to claim any value as a root, put that value in the function and you must get answer equal to 0. If it is happening, then it is a root, else it is not a root. Okay, but if we cannot find the root, what should we do in this case? So obviously common sense says, okay, if we cannot find the exact value of the root, is it possible that we can get something very close to that root, in which function is not exactly 0, but maybe it is very close to 0? For example, there is a value f of x equal to something. For example, I claim that, okay, the exact root for a problem is, for example, 2, just for understanding, rough work. And you put that 2, so you will get 0, exact 2. But you don't know how to compute that 2 for this polynomial or any transcendental equation. So what you can do, you said, okay, let's try to approximate. So what you did, you somehow managed to find a root by certain logic, which we have to learn in this method and other method as well. For example, you will get answer 1.99 something. So we know that if I put 1.99 into the same equation, I will never get going to get exactly equal to 0. It is something close to 0. For example, it may be 0.0000 or something 0.00000 something, or something very small. But in that case, we can say that it is 0, which is very small, but mathematically this is not equal to 0. Okay, so this is not a root, but this means that this value is very close to the 0. So we can say that 1.199 is a very good approximation for this unknown value which we don't know. So if we think that is 1.99 is good for our rest of the calculation, we can use it. If not, then we will try to find a much better approximation. So that is the basic concept of the approximation. That is, if you cannot compute the exact root, try to find something which is very close to that root. Okay, so this is all the method that we are going to discuss onward, is relying on this concept. However, to achieve that thing, every method has its own logic, and they are dealing with their own strategy. So due to which we have some drawbacks of each method. So let's start the first method, and I will just try to explain the concept of this method. Similarly, I will discuss the other method in the next class, and so on. And after that, I will solve a one example based on the all these methods, so that you can compare all the comments that I have made during the lecture, that which one is better, which one is slow, all these things. Okay, so let's continue. The first method to finding the roots of the equation is called uh, bisection method, or in other words, sometimes it's called interval halving. You will just learn it why we call it interval halving. So let's consider a nonlinear nonlinear equation y equal to f of x. So whenever I say nonlinear, I do not need to explain whole story behind it. Okay, so we have given a one function. It could be a polynomial or transcendental, and we need to compute. We need to compute its root. Okay, we will discuss method only for one root, but if the equation has a more roots, then we can start repeating the same process. So since those methods that we are just covering, they are also implemented in calculators as well, because as I told you that there exists no high, once the degree crosses at the higher order, we do not have an exact method to find the root, but calculator provide us, but they are not exact answer, they are approximate computed to best of their knowing. So what are the methods that are doing this? So these are the methods that we are discussing there. Okay, obviously these are very basic methods. Their advanced versions are implemented, but that's why you got the answer most of the time. But let's say, so concept is we are taking a one equation which could be a polynomial or transcendental, and we our target is to compute its one root. Once we learn the process for one root, we can repeat this for as many as root we can have. Okay, that so let exact root, it is just for explaining, let exact root of y equal to f of x is xr. Now question may arise, sir, if you know the exact root, why we have to learn this method? Okay, it is a derivation, so we are assuming that, let's say there exists some number xr which belongs to the domain of this function, whatever be this function, and such that, okay, this is the root. That is, in short, instead of this whole sentence, I can write it simply like that. If I replace f xr in the f of that function, the answer must be equal to 0. This is exactly equal to 0. Okay, so this is our exact root. Okay, so so what we are doing now, so I have to draw a graph. It is not a derivation very lengthy, it is very simple derivation, but we need to understand in the form of a graph. So what I'm doing now, student, this is the equation for which I have to find the root, but I do not know how to do that. So what I'm doing here, I am just plotting that graph equation on the x-axis. Okay, x, and this is y, and this is y negative, and obviously this is origin, and you are already thinking correct. I can extend it into the second and third quadrant as well, but the concept that I want to explain will be sufficient to explain with the one and fourth quadrant, but we can whatever we are learning here can hold for other quadrant as well, so it does not add much anything. So I'm not going to this part, but the concept could be explained from the only this quadrant, but there is no need to only discuss it with this quadrant. You can have a same analysis from the other quadrants as well. So this will be clarified to you in just a moment. So what I wanted to say that, okay, this is the equation whose root I cannot find easily with direct method, but I can plot that value. So we have learned it many times. So we are just putting some points in it and we will get the graph. So let's say the graph of this function will be something like that. You will see this type of graph many times whenever I explain the method, but this is just a dummy graph, like it is not representing exactly any function. So what I did, I plot that function. Okay, obviously we have to find the root. The graph of the function must cut the x-axis, because we just learned the fact that if this cut the x-axis, then the value must be 0. Okay, because all the values of y above this line are positive, and below this dot or x-axis is the negative. So there must be a 0 between x y values on this line. Okay, so as we assume that there is a exact root xr, so graphically if I want to show that, this must be lying somewhere there xr. You all agree with it, because this xr has a characteristic. Okay, if I put that in an equation, I will get exactly equal to 0, but I don't know that value. Keep in mind. Okay, so we have to trace that xr. That's our logic. How we will do that in the case of bisection method, it is very simple strategy. Okay, The strategy is quite simple. What you have to do, you have to do a something called bracketing. What you have to do? Something called bracketing of a root. Again, we are discussing it with respect to one root, but the same concept could hold for any other. So we have to bracketing the root. Bracketing means what we have to do, we have to understand a very simple logic. So if I select two values, let's say A and B, and both belongs to the domain, they are not necessarily a root, but let's say I have selected two values A and B, and I said that they both belongs to that function. Whenever I say belongs to the function, this means that all the definition of the function holds on A and B, and there exists some value. So what I can do, I can compute f of A, okay, and similarly I can compute f of B as well. What I did, I just put this A into this function and B into this function. And if I multiply those two quantities like f of A into f of B, so there are 2 points, let's say 1 to 0.1 or minus 0.2, you can understand any of the 2 points. And then what I did, I multiply those 2 points, the values of the function at these points, f of A into f of B. So I have a three possibilities to get the answer. One is I will get answer of these two product is less than 0. I may get equal to 0, or I will get greater than 0. I have a three possibilities. So okay, so I have a 1 point, second point, both belongs to domain. I put them in a function, I will get the answer of y. Corresponding to this point, I multiply those points. So I will get a one answer. So this is the one answer. So this answer could be of three possibilities. Either it is negative, that is less than 0, a positive, that is greater than 0, and equal to 0. Okay, so what does this means? Okay, what does this means? So for us, this has a very importance here. Student, if you have a 2 point selected and you have a this condition f of A into f of B equal to 0, this means that the at least one of A or B is a root. Why? Because if I multiply two things and answer is exactly equal to 0, this means that either this is 0 or this is 0. That is, if f of A, f of B equal to 0, this implies either f of A is 0 or f of B is 0. You got it? Either f of A or f of B is 0. If f of A into f of B equal to 0. Okay, so what should we do in this case? So there is no need to do anything because you have selected to a root of this equation, because if it is equal to 0, this means it is a root. So either A or B or both may be a root of the equation. So you do not need to apply any method. So this is the one of the easiest case where we do not need bracketing because we already find the root. So there is no need, because this is equal to 0 means it is a root. XR equal to A or XR may be a B, that is equal to a root. So this case is not good for the bracketing purpose. Okay, what if I'm continuing the bracketing topic here, but diagram I will use little bit later. There is not much derivations involved in this. Okay. So number two, if in fact, I think student we should end the lecture here, and because I will continue the lecture in the next lecture at the beginning 6A, but this is the end of the lecture number 5C. Thank you for your time. Okay, student. So in the last lecture, that is in a 5C, what we have done, we have discussed one part where we say that if this is equal to 0, then either A or B is 0. That is, one is the value is the root. So we do not need to bother much. But what if f of A, f of B is greater than 0? If it is greater than 0, we know that both have a same sign, because we cannot get a value greater than 0, positive value in fact, when f of A and f of B both has the same sign. What are the possibilities for either both are positive or either both are negative? Okay, so if if I selected 2 points A and B, then in this condition, we will have a root or we do not have a root. We don't know it. Why? What does this mean? It means that if I selected A and B such that if I put them in a function, I will get positive answer on both the points or a negative answer on both the points. Not positive, negative, only positive or negative. This means that if I multiply them, I will get answer greater than 0. So if it is greater than 0, that is positive. Then in this case, I have no conclusion about whether there exists any root between A and B or not. That is, we have managed to a bracketing or not. Because usually there exists no root, but there is a chance that there may exist more than one root as well in this particular case. So this is not a confident way. So in this case, what we have a conclusion, if this is the case, then A and B may or may not contain root. Okay, this is a confusing. So just to I let this diagram is like that. I will explain this part which I have just explained by the diagram. When this will happen. For example, I have a function like this, and I selected 2 points A and B here randomly. This is a graph of y equal to f. To compute f of a, what I have to do, I have to put this a into this equation. So I will get this height, and this point is f of a. Similarly, I put b there, I will get this height, and this point is f of b. So I'll get these two. So if I multiply this f of a into f of b, so what will I get? F of a, f of b. Okay, but both are on the positive y-axis. So whatever be the magnitude, we are not interested, but we know that they have a positive sign. So if I multiply them, their answer is also positive. This is greater than 0. So in this particular situation or a case, we do not need to bother much for the roots bracketing because we have bracket the root. Because there is, however, we can see that in the interval A and B, there is no root. Okay, but for now assume that this line A is not exist here. This is not the point. I have a point which is going there. Okay, so if I selected A somewhere there, A, because it is random, we have to choose ourselves. So f of A. So now if this is no